Okay, hello, this is chapter 17 and now we're talking about metals. So we'll be discussing physical and chemical properties of metals. In order to know that, we have to remind ourselves about the structure of metals. So we've done this before, but you should remember that when you're asked to explain the structure of metals, you should remember to say that metals have a giant three-dimensional structure in which regular rows of positive ions are surrounded by a sea of free-moving electrons. So we said metals basically are solids, so they are made up of regular rows of something. Now, regular rows of what? Since the metals, each atom has 1 or 2 or 3 electrons in its outer shell, because we said metals are basically in group 1, group 2, group 3, and everything in between. So each atom has 1 or 2 or 3 electrons in its outermost shell that it really doesn't want. So these outermost electrons are sort of floating around the atom. So the atom is no longer a neutral atom, it is now a positive ion. So these are arranged in regular rows, close packed like any other solid, but they are also surrounded by a sea of delocalized electrons or free-moving electrons. Remember that sometimes you will be required to draw this kind of diagram to show the structure of metals. Okay, so this is a typical question that you could have about structure of metals. So a question could say, a student draws this label diagram, show the particles in magnesium metal. He makes 2 mistakes in this diagram. State the 2 corrections he should make to his label diagram. So what's wrong with this diagram? This is a diagram of what? Of magnesium metal. Now, metals, we just said, are what? They are regular rows of positive ions, not positive and negative, positive, negative, positive, negative. And then they're surrounded by a sea of delocalized what? Delocalized electrons. So the 2 mistakes in this diagram is that, first of all the ions should be positive, not positive and negative, and it is surrounded by delocalized electrons, not protons. If we're asked physical properties of all metals, you should remember all metals conduct electricity, all metals are malleable and ductile, all metals are shiny. These are properties of all metals, there are no exceptions. So all metals conduct electricity, and if we say why they conduct electricity, that is due to presence of free moving electrons or presence of the delocalized electrons that are free to move. All metals are malleable and ductile. Do you remember what is meant by malleable and ductile? We said malleable means we can spread them into sheets like your aluminium foil that we have at home, and ductile means they can be pulled into wires like the copper wires that we have at home. So all metals are malleable and ductile. Why is that? Because the layers of positive ions that are present in the metals can slide over each other when heated or hammered. And of course, all metals are shiny. And if we're asked about the appearance of the metals, we usually say they are silvery appearance or silvery color. This is another typical question you could be asked. Explain why magnesium metal is malleable and a good conductor of electricity. So we said it is what? It's a good conductor of electricity because it has free moving electrons. Remember, the only one that we say free moving ions is if I'm talking about an ionic compound. But this here is a metal, so it has free moving electrons. Now we said metals are malleable because layers of positive ions slide over each other when heated or hammered. Okay, so that was the physical properties of metals. Now, if we talk about the chemical properties of metals, we need to talk about chemical reactivity series. So the reactivity series is just an arrangement of metals showing which one is more reactive than which. But even without knowing or memorizing the chemical reactivity series, you can deduce this from the periodic table. So just looking at the periodic table, you know that everything in group 1 is more reactive than group 2, and group 2 is more reactive than group 3, and group 3 is more reactive than transition metals. So, and within the same group, the one below is more reactive than the one above. So if I say in group 1, potassium is more reactive than sodium, so we say K and then Na. In group 2, we have calcium more reactive than magnesium, because calcium is below magnesium in the periodic table. Then we say calcium and then magnesium. And then group 3 has aluminium. Now we include in the chemical reactivity series, we include carbon and carbon monoxide, because we're going to compare their reactivity at some point later when we discuss it. And then we go into the transition metals, which is more reactive than which in the transition metals. Zinc is more reactive than iron, more reactive than tin. Remember that the chemical reactivity series includes the metals that are normally used in reactions. So some of the metals in the periodic table are not usually used in reactions, but the chemical reactivity series arranges the reactivity of the ones that we normally discuss. And then we put hydrogen, also because we're going to compare the reactivity of metals to hydrogen at some point. And then below hydrogen, we have the metals that are not very reactive. So we have copper, silver, and gold. These are below hydrogen in the reactivity series. So this is the chemical reactivity series: Kanaka, Magal, zinc, iron, tin, and then copper, silver, gold. If you don't memorize it, check in the periodic table as I told you. Okay, then we talk about the different reactions of metals. This is what we mean by chemical properties of metals. So first of all, reaction of metals with oxygen. So if I have a gas jar like the one in the diagram, and I have a gas jar spoon, and I put the metal in the spoon, lower it into the gas jar, light it, allow it to burn in oxygen, any metal will react with oxygen to form its oxide. So sodium forms sodium oxide, magnesium forms magnesium oxide, and of course we said the reactivity depends on the position in the group. The one below in the group is more reactive than the one above. You have to know that when we burn magnesium in air or magnesium in oxygen, first of all, what does it give you? It gives magnesium oxide. Now, what are the observations when I do this kind of reaction? Remember that the observation is when magnesium burns, it burns with a bright flame or a white flame. And then it forms what? It forms magnesium oxide. You should know that magnesium oxide is a white solid or white ash. Okay? You should also remember when we talked about acids and bases, we said that oxides of metals are usually basic. That means if you dissolve them in water, they form an alkaline solution that contains hydroxide ions. But we also said that some metals have amphoteric oxide. Do you remember the meaning of amphoteric? We said amphoteric oxide is one that can act both as an acid, so it will react with a base, or as a base, so it will react with acid. And remember from the chapter on acids and bases, we said which ones form amphoteric oxides? Aluminium, zinc, and lead form amphoteric oxide. So aluminium burns in oxygen to give aluminium oxide. Now this aluminium oxide can react with acid, so in this case it's acting as a base, and that forms aluminium chloride plus water, so it still forms a salt plus water. Or it can act as an acid, so it reacts with a base like sodium hydroxide. In that case, the salt is something called sodium aluminate plus water. This is another question that you might have, so you could be asked this question. A student uses this apparatus to find the mass of magnesium oxide that forms when a strip of magnesium ribbon is burned in air. So usually this kind of experiments, we put the metal inside a crucible and we cover it with a lid and we heat it. So the metal turns into its oxide, and then I can weigh it, or I weigh the crucible and lid at the beginning and then weigh it at the end and things like that. Now, the first question that you have here says, describe the appearance of the freshly cleaned magnesium ribbon and the appearance of the magnesium oxide that forms. Magnesium ribbon is a metal. We said, what is the appearance of a metal? The appearance of metal is silvery. Okay, what was magnesium oxide? What was the appearance of magnesium oxide? You have to remember, it's a white solid or white ash. Explain why the student lifts the lid and quickly replaces it several times during the experiment. So when we do this kind of experiment, first of all, I have to cover it. I cannot leave it open to the air. And then after some time, I need to remove the lid, open the lid, and then close it again, open the lid and close it again. So what am I doing? Why am I doing this? I lift the lid from time to time. Remember that the magnesium is trying to react with what? It's trying to react with oxygen. So at some point, I don't want it to run out of oxygen. So I open the lid to allow more oxygen to react with the magnesium. Now, why do I have to cover it? Can't I just leave it open? No, because we said what is formed is magnesium oxide, and the magnesium oxide is white ash that can escape from the crucible. So this is to prevent loss of the product from the crucible. This is another possible question that you might be asked. Lithium is stored in oil to prevent it from coming into contact with air and water. Remember this, that metals in group 1 are very reactive. When they are exposed to air and or water, they react very quickly. So when I store them, they have to be stored under oil. So things like lithium and sodium and potassium, if we store them in the lab, they have to be stored under oil. This is to prevent them from reacting with the oxygen and water vapor in the air. So the question says, when a piece of lithium is removed from the oil, dried and cut, the exposed surface, so remember that I cut the lithium, this is a metal in group 1, and you remember that metals in group 1 are soft metals, so you can cut them with a knife. Now, once you cut them, the surface of the metal is just like any surface of a metal, so that is shiny. But if I leave it exposed to the air, what happens? It will react with the oxygen and water vapor in the air, and it will change from shiny to dull. Okay? It will not form bubbles because it's not reacting with something to give a gas. It will not burst into flames. This is not cesium or potassium. Remember that lithium is at the top of group 1, so it is less reactive than cesium or potassium. Cesium might burst into flame, but lithium would not. Does not change, that's not a correct answer. So your answer is changes from shiny to dull. Okay? Now, let's try talking about reaction with cold water. So here we're talking about reaction of sodium with cold water. So if we put a piece of sodium, it has to be actually a very small piece of sodium, into a beaker containing water, what happens? First of all, if I look at the reaction, I'm going to say that sodium is a reactive metal, so it reacts with cold water. And I'm going to tell you that any metal that reacts with cold water gives the hydroxide plus hydrogen gas. So sodium in water will give sodium hydroxide plus hydrogen gas. Now, what do we see when we put this piece of sodium in the water? First of all, sodium is in group 1. It has low density, so it floats on the surface of the water. Now, when it floats, it is reacting with the water and is giving out bubbles of hydrogen gas. So these bubbles of hydrogen gas will keep pushing the sodium around on the surface of the water. So we say that the sodium floats, darts means moves around on the surface of the water, and then it melts or disappears because it is going to react and it will become smaller until it disappears. Also, the bubbles of gas that are giving out are hydrogen gas. So you will see vigorous fizzing or bubbles of gas that are coming out very quickly. Now, the gas that is coming out is hydrogen gas, and hydrogen gas is flammable. So the bubbles of hydrogen gas may catch fire. If we want a fourth observation, remember that these are the 3 most important observations, and he will ask you, what are the observations when sodium reacts with cold water? A fourth observation would be the fact that because it gives sodium hydroxide as a product, then the solution is alkaline, and that means if I put litmus paper, what happens? The solution turns litmus paper to blue because the solution is alkaline. Okay? You have to know the observations when we put sodium in cold water. So this is a typical question. An example of a question would be, a teacher investigates the reaction between sodium and water. The teacher fills a trough of water. She adds a few drops of litmus solution to the water and then adds a piece of sodium. So she's doing the experiment that we just talked about. The sodium floats on the water. Yes, we said that. It reacts with the water and produces bubbles of hydrogen gas. Yes, that's correct. Now he's asking you to state two other observations that are made. So what were the other two observations? He has already said floats. He has already said bubbles or fizzing. So you can't say fizzing. So you can say the sodium darts and melts. And the litmus solution, because he says that he has litmus solution in the water. The litmus solution turns blue. Okay? This is another typical question that you may be asked. Balance the equation for the reaction between sodium and water. Include state symbols. What is the state symbol for sodium? Sodium is a metal, so it's solid. What was the state symbol for water? We said water is always a liquid. Sodium hydroxide is something that dissolves in the water, so that is aqueous. And hydrogen is a gas. And then you need to balance. Can you understand how to balance? You should know how to balance. So one sodium before the arrow, one sodium after the arrow. Two hydrogens before the arrow, three hydrogens after the arrow. So that means that I need to put a 2 in front of the water and a 2 in front of the sodium hydroxide. That makes it 4 hydrogens, but that has ruined the sodium, so the sodium needs a 2 in front of it. Now everything is balanced. Remember, do not leave an equation without balancing, even if he doesn't tell you to balance. Lithium and potassium react in a similar way to sodium when added to water. State why they have a similar reaction in terms of electronic configurations of their atoms. So, what is common between lithium, potassium, and sodium that makes them react in a similar way? In terms of electronic configuration. Electronic configuration means in terms of the arrangement of the electrons. So, the fact that they have, all of them have one electron in outer shell because they are all in group 1, so they all react in the same way. Now, place the elements, lithium, potassium, and sodium, in order of reactivity. Do you remember the reactivity? If you don't remember the reactivity series, you can just check the periodic table. You will find that potassium is at the bottom, sodium, lithium, and we said the one at the bottom is the most reactive. So, potassium, sodium, lithium, that is the arrangement of the reactivity. Okay? Another possible question. The table below lists some statements about the reaction of cesium with cold water compared to the reaction of lithium with cold water. So he's comparing lithium to cesium. Remember, we said, where is cesium? Cesium is at the bottom of the group 1 in the periodic table. So which one would be more reactive, the lithium or the cesium? Of course, cesium is at the bottom of the group 1 in the periodic table. So cesium should be more reactive than lithium. So he's saying, I'm comparing cesium to the reaction of lithium. The first choice is the reaction with cesium is more vigorous. Is that correct? Yes, of course it is correct, because cesium is more reactive since it is at the bottom of the table 1. The first group. The reaction with cesium produces a different gas. Is that correct? No. All of them, all the metals will react with cold water to form hydrogen gas. The reaction with cesium produces an acidic solution? No. We said what is formed when you react with cold water is cesium hydroxide, and that's alkaline, not acidic. The reaction with cesium produces a different compound? Yes, of course, because cesium will give you cesium hydroxide, while lithium will give lithium hydroxide. The reaction of cesium is endothermic. Do you remember what we mean by endothermic? Endothermic means you need to heat it in order to react. It takes in heat. Or is it exothermic? It gives out heat. No. Reaction of cesium with water is not endothermic. It is exothermic. Now, the next question says, write a chemical equation for the reaction of cesium with water. Again, we said cesium with water, because this is cold water. It will form cesium hydroxide plus hydrogen, and then you balance in this way. Okay. Reaction of calcium with cold water. So calcium, if it reacts with cold water, it will give exactly the same. It will give calcium hydroxide plus hydrogen. So what am I going to see now? In this case, calcium is in group 2, so it is heavier than water. It is denser than water, so it will sink. So my first observation is that calcium will sink, not float like sodium, but it will still give hydrogen gas, so I will still have strong fizzing, and the solution becomes milky because the calcium hydroxide that is formed is not very soluble in water. So slowly I'm forming some sort of white precipitate, so that makes the solution milky or cloudy. Now, when we go to the less reactive metals, because magnesium is less reactive than the calcium, it will not react with cold water easily. If I put it in cold water, the reaction is too slow. It will still give magnesium hydroxide if it's reacting with cold water, but it is very slow. Now, if I want the reaction to be quick, I have to heat it. That means the water has to be in the form of steam. So I heat the water-soaked cotton wool. The water vapor or the steam passes over the magnesium ribbon that has been heated. Again, remember that the magnesium, when it is heated, it burns with a bright flame. And then what is formed? Magnesium oxide, not hydroxide. So a metal that reacts with cold water gives the hydroxide. A metal that reacts with steam will give the oxide, magnesium oxide plus hydrogen. So again, my observations would be that magnesium burns with a bright flame. Magnesium oxide is a white solid, so a white solid is formed, and hydrogen gas is formed, which burns, or we have bubbles of hydrogen gas. When zinc reacts with steam, again, zinc is less reactive, so it does not react with cold water, it reacts with steam. And we said when a metal reacts with steam, it forms the oxide. So this forms zinc oxide plus hydrogen. So any metal that will react with cold water forms hydroxide. So this is the ones in group 1 and the bottom of group 2. React with cold water to give hydroxide. The less reactive metals like group 3 and the transition metals, they react with steam, but when they react with steam, they form the oxide, not the hydroxide. Okay? Remember that metals below hydrogen in the electrochemical series, metals that are less reactive than hydrogen will not react with water at all. So if I put copper in water, it does not react at all. Okay, metals with acid. So metal with acid gives hydrogen gas plus a salt, depending on which metal. So something like magnesium plus HCl will give hydrogen gas, and anything that gives a gas gives bubbles of gas. Now, the more reactive the metal, the more the bubbles. So for example, magnesium is more reactive than zinc, so the bubbles that I see when I react the acid with magnesium is much more than the ones formed when we react it with zinc. Now, if I put copper in acid, no reaction, no bubbles at all. Again, remember, copper is below hydrogen in the reactivity series, so it does not react with water, it does not react with acids. You can't say copper plus an acid. So, a typical question. Give 2 observations that are made when a piece of magnesium ribbon is added to acidic solution. So, you put magnesium in acid. What 2 observations would you see? Again, we said if I put magnesium in acid like HCl, for example, it gives hydrogen gas, right? So what I see would be bubbles of gas. Now, what's the other observation? The other observation is that the magnesium as a solid that I put into the acid, eventually it will start to dissolve, or it will disappear, or it will become smaller. Okay, so we say the magnesium solid dissolves, or disappears, or becomes. Another possible question that you could see would say something like this. Magnesium is a reactive metal. Its reactivity can be seen in its reactions with oxygen and dilute sulfuric acid. And he gives you 2 reactions. One with oxygen to give magnesium oxide, and one with sulfuric acid to give magnesium sulfate plus hydrogen. So the first question says, in reaction 1, some magnesium is ignited and then placed in a jar of oxygen gas. State 2 observations that will be made. We said, what are the observations that we see when we burn magnesium in oxygen? Again, we said the magnesium burns with a bright flame and a white solid is formed because magnesium oxide is a white solid. The other question is a possible question that you could have. In an experiment, a student adds a piece of zinc to some dilute hydrochloric acid in a test tube. So he has a piece of zinc in dilute hydrochloric acid. The student measures the temperature before adding the zinc. After adding the zinc, he stirs the mixture and measures the highest temperature. And then he wants to find out if there is a relationship between the reactivity of a metal and the temperature rise. So he repeats the experiment 4 times using a different metal each time. So basically, he's putting different metals into the acid, measuring the initial temperature and the final temperature so he can determine how much rise in temperature there was. Okay, so state 3 factors that the student should keep constant in each experiment. So what should he should be changing only the type of metal. But he shouldn't be changing what? He shouldn't be changing the surface area of the metal, the concentration of the acid, the volume of the acid. Remember that surface area of the metal means I shouldn't use one metal in the form of big pieces and the other metal in the form of powder, for example. They should be the same surface area and they should be the same mass of the metal. So you can either say same surface area of metal, same mass of metal, and then the acid should have the same volume, the same concentration. Using information from the table, state the relationship between reactivity of a metal and temperature rise. So what was the table? This was the table. So magnesium, gold, iron, calcium. What type of reactivity, or what is the arrangement of reactivity of these metals? You should realize that we said calcium is more reactive than magnesium, and then these are more reactive than iron, and then gold was at the bottom of the reactivity series, and we said it's not very reactive. So when they put it in acids, they found that the more reactive metal is the one that gives higher temperature. So remember that more reactivity is indicated by what? Is indicated by more bubbles of gas or by more rise in temperature. So the more reactive the metal, the greater the temperature rise. State why there is no temperature rise when gold is added. Since there is no temperature rise, this means that gold does not react with the acid. Another typical question that you could see would say the diagram shows how a student attempts to prepare some hydrogen gas. State why no hydrogen is produced. Look at the diagram and tell me, why do you think he didn't get any gas? If he didn't get any gas, that is just because the silver did not react. And why doesn't it react? Because it is below hydrogen in the reactivity series. So he's reacting it with silver. Remember that we said anything below hydrogen in the reactivity series will not react with water or acid. So which metals do we have below the reactivity series? We have copper, silver, gold, and we also have mercury at some point. So silver does not react with acids because it is below hydrogen, or it is less reactive than hydrogen. Which of these pairs of chemicals could be used to safely prepare hydrogen? To prepare hydrogen, that means they have to react with the acid to form hydrogen. And I don't want it to be too vigorous because he wants it safe. So the first option here, A, says copper and acid. Remember that we said both copper and gold and silver are below hydrogen in the electrochemical series or the reactivity series, so they will not react with acids or with water. Now, that means I have a choice between potassium and zinc. But potassium is in group 1. It is a very reactive metal. If I put it in acid, it will sort of explode or very violent reaction. Zinc reacts, but it's not violent, so that would be our choice. Okay? The other type of reactions that we have are displacement reactions. A displacement reaction means a more reactive metal will push the less reactive metal out of its salt. So if I have zinc plus copper sulfate, if I have a reaction, that means that zinc is more reactive than copper. If we do this for two metals and they don't react, that means that zinc is not or is less reactive than copper. So when I put zinc in copper sulfate, it will react because zinc is more reactive than copper. What does it give me? It gives me zinc sulfate plus copper. Now, can you see the original color of copper sulfate? You should know that the original color of copper sulfate solution is blue. But zinc sulfate is colorless. So one observation that you would see is that the fact that the blue color of copper sulfate changes to colorless. Also, I started with zinc solid and the zinc reacted in the copper sulfate, so at some point the zinc will dissolve or start to disappear or become smaller. And then we're forming what? We're forming copper. Copper metal, you should remember, copper metal is the red or reddish brown metal. So when it forms copper, it forms a red precipitate in the test tube. Can you see that? So these are the observations when you put zinc in copper sulfate. Now, another example of displacement reaction would be magnesium plus copper carbonate. Magnesium is more reactive than copper, so it will displace it from its salt. The copper carbonate is originally a green color. When it changes into magnesium carbonate, it is now a compound of group 2. Compounds of group 2 have no color. So the solution becomes colorless, and I will start to see a reddish precipitate of copper. Okay? A typical question. Let's take a look at what type of question we have. So here he says, in an experiment, a piece of zinc metal is placed in a beaker containing copper sulfate. So he was talking about here he's talking about the reaction between zinc and copper sulfate. The reaction that occurs shows zinc is more reactive than copper. State two observations. So what are two observations that I will see when I put zinc in copper sulfate? We said the original color of copper sulfate is what? Blue. So we said the blue solution turns colorless and the zinc metal begins to dissolve or disappear. The diagram shows two ways in which potassium can be converted into potassium chloride. Give the names of X, Y, and Z. So let's take a look at this flowchart. He starts with potassium. He heats it in gas X to form potassium chloride. So, which gas do I react with potassium to form potassium chloride? I need chlorine. Okay? Okay. Then he says he added water to potassium and he got a colorless solution of Y. What happens if I add water to potassium? We said potassium is a reactive metal. It reacts with cold water. So what I form would be potassium hydroxide. And then this potassium hydroxide, he wants to react it with an acid to form potassium chloride. Which acid should I add to potassium hydroxide to form potassium chloride? Hydrochloric acid, the acid that has chlorine in it. And notice that the question said, give the names of these, so I have to write the names of these. You shouldn't write the formulas, and if you do decide to write formula, please write the correct formula. But if he says name, give him name. When sodium is burned in iodine gas, sodium iodide is formed. Write a chemical equation for the reaction between sodium and iodine. So I'm going to write a chemical reaction, sodium plus iodine, to give what? It should give sodium iodide. Sodium has a valency of 1 and iodine has a valency of 1, so I don't write a 2 under any of them. Have I finished? No, I have to balance the equation. Even if he doesn't say balance, the chemical equation means it has to be balanced. So you need a 2 to make the 2 iodines and a 2 here to fix the sodium. Okay. The next thing we're talking about is rusting of iron. Remember that iron, when you expose it, iron is originally silver in color. So this nice clean chain on the right side is clean iron that hasn't rusted. But when you expose it to the atmosphere, it turns into reddish brown, as we can see. So this is called rust. This reddish brown cover on the iron is called rust. If we're talking about iron, we call it rust. If we're talking about any other metal, we call it corrosion of iron, of the metal. So all metals corrode. Corrode means they react with water and oxygen in the air. But when we're talking about iron, we can say corrosion of iron or rusting of iron. We don't say rusting of any other metal. Now, what do we need for the iron to rust or for the iron to corrode? We can have an experiment like this in which we have nails and we have them in different things. So when they put nails in distilled water, and you should remember that distilled water means water that has oxygen dissolved in it. Any normal water that we have has a little bit of oxygen dissolved in it. So when we put the nails in distilled water, the nails rust. Distilled water contains both water and oxygen. Now, if I put the nails in boiled water, now what is boiled water? Boiled water is water that I have boiled, so all the oxygen dissolved in it has escaped. When you boil the water, the dissolved gases go out. So dissolved oxygen has gone out. It doesn't have any dissolved oxygen, and I'm covering it with a layer of oil to make sure that no more oxygen dissolves in it. Now, when we put the nails in the boiled water, that means I don't have any oxygen. I find that the nails will not rust. Now, if I put the nails in another test tube that contain anhydrous calcium chloride, you should remember that anhydrous calcium chloride is something that absorbs water vapor from the air. So basically this test tube has no water, and if I leave the nails in this test tube, the nails will not rust. If we put the nails in seawater, now what is seawater? Seawater has water and oxygen and salts. So I will find that in seawater, in the presence of salts, or sometimes in the presence of acid, the nails will rust very quickly. So salt makes the nails rust quickly. So what does the iron basically need in order to rust? The iron needs both water and oxygen. If you're missing any of them, then the nails do not rust. So the iron requires both water and oxygen in order to rust. Now, what is rust? Rusting means that the iron changes into iron 3 oxide, or actually it is hydrated iron 3 oxide, which is the reddish brown flaky cover on the iron. So what is rust? It is hydrated iron 3 oxide. That means the iron is changing to iron oxide, and that means that this rusting or corrosion is actually an oxidation process, right? And then if we say what is the appearance of rust? Rust is reddish brown and flaky. What do we mean by flaky? Flaky means it can peel off, it can fall off. So this piece of nail, if I leave it for a long time, the rust that forms on it can peel off, and if the nails are left long enough, they will eventually just change into a reddish brown powder because all of the rust peels off. Okay, so what do we do to prevent rusting? I don't want my iron objects to rust. So what should I do? The first thing that we normally do, or the easiest thing that we normally do, is painting. So if I have railings, these are railings, the ones that we hold on when we go down the stairs, or gates, iron gates, or windows, the normal thing that we do is paint. Now, painting, what does painting do? Painting covers the iron so that it prevents it from reacting with oxygen and water vapor in the air. But the problem with that is if the layer of paint is peeled off or is scraped off, that piece of iron or that part of the iron will again start to rust. So it is something that has to be done a lot. Another method of preventing rusting would be to coat with oil and grease. When do we use coating of oil and grease? We use it when we're talking about machines. So if I have a machine in which I don't want these pieces of iron to rust, or if there is a lot of friction between them, I coat them with oil or grease. Another method would be coating with plastic. Now, when do we use this? In your dishwasher, the racks in the dishwasher that you put your dishes on, these are pieces of iron that are coated with plastic. Again, why are we coating it with plastic? To prevent the iron from reacting with water and oxygen in the air. The problem again is if the piece of plastic is scraped off or is removed, that exposed surface will again start to rust. Okay, a better way of preventing rusting would be what we call galvanizing. Galvanizing means covering the iron with a layer of zinc by dipping or spraying. So these are iron pipes, for example, or iron tubes of some sort. I want to prevent it from rusting, so I can dip them into liquid zinc. So that container contains zinc that is molten zinc, and I dip the iron into it, or I can spray it with zinc. The zinc covers the iron. This process is called galvanizing. It prevents rusting because that outer layer of zinc is a metal that is more reactive than iron, so the zinc will react and lose electrons and be oxidized instead of the iron. And the good thing about it is, even if part of this layer of zinc is scraped off, still the iron will not rust so long as any part of it is still touching the zinc. So long as there is still some zinc attached to the iron, it is the zinc that will be oxidized, not the iron. Do we understand this? So, covering with a layer of zinc by dipping or spraying, that is called galvanizing or galvanization. How does it work? The zinc is more reactive than iron, so it loses electrons and becomes oxidized instead of the iron. And the advantage is, even if a piece of the zinc is removed, still, so long as the iron is touching some zinc, it will not rust or it will not corrode. Okay, another method is sacrificial protection. Now, sacrificial protection is basically the same idea, but instead of covering with a layer of zinc, I just attach a block of a more reactive metal to the steel or to the iron. For example, in ships, the ship is made of iron. I don't want the ship to corrode, so I just put a zinc bar, attach it to the side of the ship. This presence of the zinc bar attached to the side of the ship prevents the whole ship from rusting. This is because so long as the iron is touching some zinc, the zinc will react instead of the iron, since it is more reactive, so it will become oxidized and lose electrons instead of the iron. So we can use a piece of zinc, or we can use a piece of magnesium, for example, bolted to the side of the ship. Another method of preventing corrosion was the electroplating that we talked about when we were doing electrons. So electroplating is a reaction with electric current, using electric current. So I attach a piece of, I want to cover my spoon, for example. I don't want my spoon to corrode, so I want to cover it with a layer of silver. So I attach it to the end of the battery, and the other end is attached to a silver rod, and this reaction is called electroplating, in which the reaction will occur and cover the zinc with a layer of silver. Of course, when we cover the spoon with a layer of silver, the silver is something that is less reactive than hydrogen, so it does not react with oxygen or water vapor in the air. This is a typical question. Name the process used to coat iron with zinc. Remind me again, what was this process called? When I cover the iron with zinc by dipping or spraying, this is called galvanizing. Another question says the diagram shows 3 pieces of iron. So he has a piece of iron not covered with anything, a piece of iron covered with a layer of zinc, and C has some of the layer of zinc peeled off. So the 3 pieces of iron are left in separate troughs of water exposed to the atmosphere for several weeks. The table shows the appearance of the pieces of iron after several weeks. So after several weeks, A was covered in a brown solid. So they did rust or not? Yes, we should know that iron as a metal is shiny when it is covered with a brown solid. That means it has rusted. Now B and C remain shiny. So that means that B and C do not rust. The brown solid contains hydrated iron 3 oxide. What is the common name for this brown solid? So the hydrated iron 3 oxide is what we call rust. Identify the 2 substances that react with iron to form the brown solid. We said iron needs to react with what in order to rust? Water and oxygen. Now explain with reference to the symbol in the box, the symbols in the box, why the brown solid does not form on C. Now which one was C? C was the one that was covered with zinc, but a little piece of the zinc is removed. So a little piece of the iron is exposed. But we still said that when a little piece of the iron is exposed, still that will not rust, so long as it's in contact with some zinc. So why is that happening? We said this is because what? Zinc is more reactive than iron. So it loses electrons instead of iron and becomes oxidized. So this does not allow the iron to lose electrons. Remember that I need to use the things that are in the box. And no iron 2 plus is formed. Remember we said when the iron rusts, it changes into iron 2 plus. So instead of the iron changing to iron 2 plus, it is the zinc that will react. So the zinc reacts, loses electrons, becomes zinc 2 plus instead of the iron. Okay, so that's the end of this chapter. Please study it well and try the questions that you have in the chapter as questions in the PDF. That is very important. It's very important to try the questions before you go to the next video that discusses the answers to the questions. Okay, thank you.